Thank you. Thank you for the invitation. Thank you for the opportunity to speak. Yeah, indeed, it's very difficult news. Yeah, for many people here. No, so my talk is going to be largely on holography and connection to relativistic hydrodynamics. So you'll see along the way what I'm trying to say. So my personal motivation for the work that I'm going to describe is to understand N=4 super N-Mill theory. So it's maybe a strange starting point for relativistic hydrodynamics. However, if you don't know anything about it, it's actually quite fascinating. So it's a non-abelian SUN gauge theory in 4 dimensions, and it has degrees of freedom, gluons, fermions, and scalar particles. It's not exactly QCD, but it sort of indeed it's a non-abelian gauge theory. It has lots of symmetry, but it's not exactly solvable. So in a sense, it's a simpler theory than QCD. And if you want to think about all relativistic gauge theories, this is quote unquote the Asian model of relativistic gauge theories. So it's useful to understand it. And many interesting finite temperature properties of the theory are not that dissimilar from QCD. Now, you can study real-time physics in this theory when interactions are strong via the methods of so-called holography. I'll talk about this so-called holography a little bit later. And there is one comment that I wanted to make is that many people in the room have heard about holography, no doubt. And it's important to remember that in many or maybe most quote-unquote real-world applications of holography, one simply pulls a miraculous quote-unquote holographic model out of thin air with no regard as to what field theory this model is supposed to describe, if anything at all. Now, this is a different with N=4 supersymmetric Yang-Mills theory because you know exactly what you're studying. When you do holography, you know what the Hamiltonian is, you know what the degrees of freedom are, you know what the interactions are. Now, so if you want to understand hydrodynamics in holography, the first thing you want to understand is you want to understand hydrodynamics of this N=4 supersymmetric Yang-Mills theory. And when I started thinking about it recently, I realized that in spite of lots of holographic works, the full hydrodynamic description of N=4 super Yang-Mills theory in holography has not actually been worked out in full detail. And to understand why, so let's look at the symmetries of the theory, because it's the symmetries of the theory that determine eventually the hydrodynamic behavior. So the symmetries, of course, translations and rotation, and so this is what gives rise to the conventional hydrodynamics that that most people are familiar with. The theory is a supersymmetric theory, so it has supersymmetry. So supersymmetry may have hydrodynamic manifestations. People have worked on that. So that hydrodynamic manifestations is not manifested in the classical equations of motion because the corresponding conserved charges and densities are fermionic. So they do not obey sort of classical equations. However, it can manifest themselves, these degrees of freedom can manifest themselves in hydrodynamic correlations, still long distance, late time correlations. And another symmetry that the theory has, it has a global symmetry. The global symmetry is a non-abelian symmetry. It's SU4, and this SU4 also has hydrodynamic manifestation. So this is what I'm going to be talking about. Now, there's also phenomenological motivation, and the phenomenological motivation comes from this called BSQ hydrodynamics. So, so this abbreviation B stands for baryon number, S for strangeness, and Q for the electric charge. And there are papers about the relevance of these BSQ degrees of freedom for the quark-gluon plasma. So these kind of BSQ models in the context of holography, they have not been worked out that much. So what we need is hydrodynamics with several species of conserved charges. So the first, before you do hydrodynamics, you have to understand thermodynamics. So here is the thermodynamic setup. So I'm going to work in R3, not S3, so space, infinite volume, grand canonical ensemble with this grand canonical density operator. And then if the theory has global conserved charges, you need to stick these global charges in here. So these charges are conserved, so they commute with the Hamiltonian. Now, what happens if the conserved charges do not commute with each other? So if you have a non-abelian symmetry, your conserved charges do not commute. So are you actually allowed to stick non-commuting charges into the density operator? So to see what happens, let's remember what happens if you want to describe, say, a rotating system that has angular momentum, say a system on a sphere that has angular momentum. You would write a partition function that looks like this, where Lz is the z component of the angular momentum. And so we normally say that, quote unquote, we can choose angular momentum of the in the z direction by rotation symmetry. Now, what these words actually mean when we say we can choose angular momentum in the z direction by rotational symmetry, so in thermal physics, this means the following. We have this density operator that looks like this. And by cyclicity of the trace, we can insert 1 in the form of r times r minus 1, where r is the rotation operator. Then this rotation operator is, of course, the exponential of conserved charges, angular momentum in this case. And by rotation symmetry, it commutes with the Hamiltonian, so you can pull it through e to the minus beta h. And then this conjugation gives you sort of group element of rotations in an arbitrary direction, where this arbitrary direction is specified how exactly you rotate your z direction into an arbitrary direction specified by this rotation operator. So this is what we mean when we say let us choose angular momentum in the z direction. So it is sufficient to choose it in the z direction because we don't lose anything. Now, more generally, if you have non-abelian global symmetry such as SON or SUN, the quote-unquote that direction will become the maximal abelian subalgebra, which typically would be U1 to some power U1 to the power n. So for SUN plus 1, the z direction will be U1 to the n, and the conserved charges that appear in the canonical density operator, in the grand canonical density operator right here, would be the commuting charges, and there will be n of them. Yeah. Okay. Yes. That's right. That's right.
Calculate something, a linear combination of something which is invariant under this kind of transformation?
Well, I guess it depends on the observable that you want to calculate. Yeah.
This argument applies to the trace itself.
That's right.
Something which is not a scalar, like J itself.
If
calculate this, in general, this is the Cartan Sabat.
Yes.
You can turn it into something which is a linear combination of something calculated with only one.
Yes. Yes, that's right. Yes.
One, sorry, the number of chemical potentials.
Yes. Yeah. So this. Yeah. No. This is exactly the argument, but that argument may sound a little bit sort of obscure. But the argument about rotations is something that everybody knows from their sort of quantum mechanics. Yeah. So as I said before, we understand hydrodynamics. Let's understand thermodynamics. So last week there were a few discussions. Not last week and the week before, there were a few talks about thermodynamic stability. So this is a very sort of poor man's, very crude discussion of thermodynamic stability. So the argument about thermodynamic stability, if you want to make it like the least formal, without many indices, obscure observables or funny spaces, looks like this. So you have your stuff in a box, and you imagine partition in this box in two. So this has entropy S of E, this has entropy S of E. So the total entropy is twice S of E. And then you imagine, like by hand, taking some energy from the left box and putting it into the right box. So the system looks like that. So once you have removed some energy from here and put it here, this has entropy S of E minus delta E, and this has entropy S of E plus delta E, and the total entropy will be the sum of the two again. Now, if after you have done this, so if the total entropy here is greater than the total entropy over here, then the original state is not an equilibrium state, because you can increase entropy by moving the energy between the two halves of the boxes. And so this means that entropy as a function of energy must obey this inequality. Okay, so this is the condition of so-called concavity. And if the sign is sort of opposite, you call it convexity. So this is kind of standard discussion that you can find in books on thermodynamics, though thermodynamics, I don't know, takes less and less role in physics, undergraduate physics curricula, and is probably the most hated subject by undergraduate students. So anyway, so this is a simple argument of thermodynamic stability. Now, so this was a global statement about sort of finite changes in energy. Infinitesimal statements about stability is given by second derivatives of thermodynamic potentials, the so-called Hessians. Hessian is just a matrix of the second derivative. So if you look at the second derivative of entropy, so you're looking at this Hessian of entropy, which is second derivative of entropy with respect to the arguments that entropy is naturally depends on, which would be energy. So this would be density of entropy. So a fixed volume, infinite volume, density of entropy, density of energy, density of charges, or you can think about these charges as different species of particles. And so this Hessian would be negative definite. So similarly, this matrix, when you differentiate energy with respect to its variables, entropy and the number of charge densities, would be positive definite. For pressure, if you work in the grand canonical ensemble, the natural arguments are temperature, chemical potential. Again, this matrix has to be positive definite. So here is a simple example of the Hessian of matrix of the second derivative of pressure. So this is partial S, partial T. S is density of entropy, derivative of S with respect to chemical potentials, number density with respect to temperature and charge susceptibilities. So this would have to be positive. This would have to be symmetric and positive definite. Now, in the language of thermodynamics, this sort of looks okay. This is natural. But in language of maybe field theory, it's something that is less familiar. So the matrix that is more familiar from the field theory point of view is this matrix, which is related to this Hessian of pressure by this congruence transformation. So why is this matrix something that is more familiar from the field theory point of view? Well, the reason it's more familiar is because this element is just mean square fluctuation of energy. So this is something that's positive because Hamiltonian is a Hermitian operator. And this element is mean square fluctuation of charge, which is again positive because charge is a Hermitian operator. So this is the cross one, and this matrix is a positive definite matrix, which is of course connected to the statement that this matrix is positive definite. A positive definite in a stable equilibrium state. Now, if you want to do now thermodynamics of a theory that has a global non-abelian symmetry, such as U SU n plus 1, so it has U1 to the power NF. NF is the number of flavors. So this is maximal abelian subalgebra that sits in SU n plus 1. The partition function is the normal grand canonical partition function with these chemical potentials and charges which sit in this Cartan subalgebra. So this A goes from 1 to n. And these charges are, of course, made out of the generators. This would be the generators of the Cartan subalgebra and the charge operators. Now, this is a partition function you have to trace over the Hilbert space of the theory. And when you take the trace, well, okay, so you're left with, so you're supposed to be left with something that's SUN plus 1 invariant. And so there are all these generators that sit here. So these generators are like normal, matrices. And so what happens to these matrices to make it invariant? So the partition function then has to become, traces, combination of traces of all these generators. So little TR is the trace in the space of these normal matrices, and capital TR is the trace in the Hilbert space of the theory. Okay. Now, these traces of generators are proportional to products of Kronecker deltas, DABC and FABC. So FABC are the structure constants of the group, right? When you compute two generators, the right-hand side of ABC times the generator. DABC is the so-called anomaly coefficient. It's the symmetric trace. It's the trace of the generator times the anti-commutator of two generators. And so for group SUN, the product of two generators can be written like this in terms of Kronecker delta DABC and FABC, and you can write the traces of more generators, 3 and more using this formula and the normalization condition for the generators. Now, what this means is because your partition function comes with products of deltas and Ds and Fs, and it also has this chemical potential. This chemical potential have to be contracted with deltas, Ds, and Fs, right? So basically you have contractions of these deltas, Ds, and Fs with like mu A, mu B, mu C, and so on. So this is the form of the partition function. Now, F is a totally antisymmetric. So when you contract it with like symmetric things here or symmetric combination of chemical potential, it essentially drops out. And so what this means that the only combinations, the only things that the partition function can depend. Yeah. The carton, just the cartons. Just the. No, but the generators compute, but it doesn't mean that DABCs are zero. So DABCs are non-zero. Symmetric traces of the generators of the carton are non-trivial. That's right. For the cartons, Fs would be zero. Yes. Yes. So so you have contractions of chemical potentials with deltas and DABC. So this means that things that the pressure can depend on, it can depend on invariants like this, things like that, and if you can write down more things with that are contractions here. So this actually gives you a significant sort of constraint on what the matrices of charge susceptibilities will look like, or what the matrices of electrical conductivities or charge conductivities, not electrical, sorry, charge conductivities will look like, because the matrices of susceptibilities are essentially given by derivatives of this thing with respect to the chemical potential, and you know the group structure of this. So here is an example. So example 3 flavors. So this would be something that's embedded into SU4. And you can choose a very convenient basis of Cartan generators where DABC is only non-zero if ABC is a permutation of 1, 2, 3. It's a choice of basis, but it's a very sort of convenient choice. And in this case, sort of the group structure that sits in the pressure here, so susceptibility is second derivative of pressure with respect to the chemical potential. So you know the group structure here. It will tell you that the matrix of susceptibilities looks like this. Essentially, all diagonal elements are equal to each other, and all off-diagonal elements are also equal to each other. So this matrix has n minus 1, so in this case it would be 2 eigenvalues, which are difference of the susceptibilities, and this corresponds to thermodynamic fluctuations of the difference of the two charges, n1 minus n2, and 1 and 3, and 2 and 3. And it has one eigenvalue, which is this, which is the fluctuations of the sort of average charge. So a brief comment on n equal 4 supersymmetric Yang-Mills theory. So if so, the theory, in the context of holography, you hear about strongly coupled n equal 4 super Yang-Mills, but it doesn't have to be strongly coupled. It's a quantum field theory. It's a conformal field theory. Coupling can be adjustably tuned from very small to very large. So if the theory is non-interacting, if it is a free n equal 4 super Yang-Mills theory, then equilibrium state does not exist at non-zero chemical potential. So the reason is that the theory contains scalar fields, and the scalar fields also carry charges under this symmetry, and these scalar fields have flat direction, so the potential is flat in some of the direction. So when you introduce chemical potential is like a negative mass for the scalar field, and because it's a free theory of flat direction, you introduce chemical potential, this quote-unquote negative mass will curve the potential downwards, and there is going to be no ground state. So a free n = 4 supermills does not exist at non-zero chemical potential. There is no equilibrium state. If the state is, if the theory is weakly coupled, then the interactions will generate a little bit of thermal mass. And then the equilibrium will not exist if the potential is sufficient, if the chemical potential is sufficiently large. Well, lambda is the coupling strength of the theory. And what happens at strong coupling, what is the fate of n = 4 supermills at strong coupling? So this is sort of a little bit of a murky business. At strong coupling and at chemical finite charge density. Yeah. Yeah. Well, I guess this would mean that if you connect it to a bath of charge, your theory will draw the charge from that bath indefinitely. So it's a statement about the grand canonical ensemble, right? So if you work in the canonical ensemble, we just fix the charge. It's a different story. So fixed charge, everything will be fine. It's just the grand canonical sort of thing. Grand canonical and infinite volume. It's a problem that arises in grand canonical and infinite volume. Well, yeah, it's a free theory, right? So yes. Yes. Yes, of course. Oh, yeah, yes, of course. I mean, this is not something that is miraculous. I just wanted to sort of to put it in a bigger context. Yeah, I don't remember. So Larry, Yaffe, and Daisuke Yamada have a paper about this in I think it was 2006, so 2008. But what they do, they study theory on a sphere. So what happens if you're not on a sphere? Mm-hmm. Yeah, but this would be still in the canonical ensemble, right? Where you fix the number of particles. Mm-hmm. 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 Yes, I agree. Well, well, in entropy, I normally define entropy in equilibrium, but if there is no equilibrium, I wouldn't know how to think about entropy. Um, yes. That's all it is. Well, supersymmetry sort of requires these flat directions for you. Yeah. So that was thermodynamics. So now let's do a little bit of hydrodynamics. So the question I want to ask is, how do thermodynamic instabilities, meaning negative eigenvalues of the Hessian, how do they manifest themselves in hydrodynamics? So there was a little bit of discussion of that in Lorenzo's talk last week. So this is going to be put in like very concrete formulas. Uh, to the general theory. So this is relativistic hydrodynamics, so conservation laws, constitutive relations. So this is normal Landau frame constitutive relations from Landau and Lifshitz. So the difference here is that this matrix of charge conductivities, the charge conductivity is a matrix now. It's not just a single charge conductivity. There are several species, U1 to the power n. So this is now a matrix. And you have to supplement this equation by the equation of state. So if you are in perfect fluid hydrodynamics, you can get away with the equation of state pressure as a function of energy and the charge density. It will close your system of equations. But if you're dissipative fluids, you cannot do relativistic hydrodynamics of dissipative fluids with this equation of state because you have chemical potential in the constitutive relation as required by the positivity of entropy production. So you actually, for dissipative fluids, you have to work with the grand canonical equation of state, which is pressure function of temperature and chemical potential. Onzaga relation will tell you that this matrix is symmetric, and the positivity of entropy production of equilibrium divergence of the entropy current will tell you that shear viscosity, bulk viscosity are positive, and this conductivity matrix is a positive definite matrix. So let's look at now simple solutions, which is linear perturbations of global equilibrium with constant temperature and chemical potential. So here is a simple example of hydrodynamic modes for one species of charge. There's d minus 1 in d space dimensions shear modes, very familiar energy density plus pressure. There's one sound wave, speed of sound, and damping coefficient of sound. There's one diffusive mode, minus I dk squared. D is the diffusion coefficient. So in a state with, say, zero equilibrium state with zero chemical potential, speed of sound is given by that. So if, remember this thermodynamic stability condition that I showed earlier, the ds dt is positive. So if this is positive, then speed of sound squared is positive. So this is a real number. So you don't have a plus minus I, so you don't have an instability here. So this will be positive by thermodynamic stability. Now, if you look at the diffusion coefficient here, then sigma is positive by the positive density, by the positivity of entropy production. And d and d mu is this charge susceptibility. This is mean square fluctuation of charge, n squared minus n squared. So this again positive by thermodynamic stability. So positivity of diffusion constant is a combination of two things, positivity of entropy production and thermodynamic stability. Now, for the dissipation damping coefficient of sound waves, the situation is somewhat different because there is no extra thermodynamic stability conditions that are required to ensure that the damping constant of sound waves is actually positive. So once you ensure that shear waves decay E plus P is positive, and once you ensure positivity of entropy production, then this is going to be automatically positive. There are no new conditions that sort of arise from there. Now, if you have hydrodynamic modes with non-zero density in equilibrium, then Vs squared is going to be more complicated, so it's sort of written like that. But you can also write it in the grand canonical ensemble, and again, it will be positive. You can show that this is going to be Vs squared is going to be positive by thermodynamic stability. Diffusion constant is also going to be similar. It's going to be proportional to the charge conductivity divided by how much. What do you mean? Yeah, your conformal is always fixed. Yeah, conformal is always fixed regardless of whether I have. Yeah. 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 Yeah, so this is going to be some, if you write it in grand canonical ensemble, it's going to be some combination of thermodynamic derivatives. But again, thermodynamic stability conditions in terms of these Hessians that I showed earlier will ensure you that this D is going to be positive if thermodynamic stability conditions, well, they do tell you that this denominator is positive and this sigma is positive by the density of production. Now, sound wave, actually the situation is again similar. Positivity of sound damping does not impose you, does not relate to any new thermodynamic stability conditions. Once you have positive speed of sound squared, once you have positive E plus P, then this is also going to be positive because the stuff that sits here, it's going to be some horrible combination of derivatives, but it's always going to be positive regardless of whether you are thermodynamically stable or not. The point being is that when there is hydrodynamics, then positive entropy production and thermodynamic instability would imply a dynamic instability of equilibrium. And so this is a trivial comment. The speed of sound has less information than the actual equation of state, and so system can happily have positive speed of sound squared and still be thermodynamically unstable. So I'll show you examples later. So what happens if you have more than one species of charge? Well, then hydrodynamic modes sort of they look exactly the same. It's exactly the same hydrodynamic modes that you know from from elementary hydro. So let me go through this hydro modes in a bit more detail. So for sound waves, for n flavors. So the speed of sound you can write down like this, but from this equation it's not immediately obvious how to sort of relate this to thermodynamic stability conditions. If you do it in the grand canonical ensemble, which you actually should do for dissipative fluids, okay. There are many ways you can write the speed of sound, many ugly and horrible ways how you can write speed of sound depending on your chosen thermodynamic variables. So this is one way to write the speed of sound with arbitrary many charge flavors. So this X is the matrix of susceptibilities. Again, this is mean square fluctuation of energy, mean square fluctuation of charges. So this and the cross terms. So this matrix X is positive definite, X minus 1 is positive definite, and S plus minus are just some real vectors made of E plus P and N, some column vectors that have E plus P and N. So written in this way, speed of sound squared is obviously positive if this X is a positive definite matrix. For the sound damping coefficient, you can write sound damping coefficient in this way. So shear bulk viscosity, E plus P, determinant of this matrix squared, speed of sound squared, and then you have sigma is the conductivity matrix contracted with some vectors which are polynomials of thermodynamic derivatives. I mean, I'm not telling you what they are. It's very easy to write down these vectors. I'm just not writing them down to clutter the slides. But the thing is, if you look at it like this, sigma is a positive definite metric. So this thing, numerator is always going to be positive definite if the entropy production is positive. And so this is always positive definite regardless of whether you have thermodynamic stability or not. So this means that in the sound channel, and for sound waves, there is no instability as long as speed of squared sound is positive and E plus P is positive. So in particular in CFT, speed of sound squared is always 1/3. So hydrodynamic sound waves are always stable. So regardless of what happens to various susceptibility matrices, sound waves are always going to be stable. There's going to be no instability. Now for diffusion, the situation is different. So if you have diffusion of n flavors, then there are n diffusion modes. And so what are the diffusion coefficients? Well, diffusion coefficients are eigenvalues of a certain matrix, the diffusion matrix. This diffusion matrix is n by n. And in a state with zero densities in equilibrium, this diffusion matrix is the inverse of the susceptibility matrix times the conductivity matrix. So conductivity matrix, conductivity, susceptibility matrix is this. In a state with non-zero chemical potentials in equilibrium, it's again, is what you have to do, you have to sort of go to the correct basis where this diffusion mode decoupled. It's sort of, morally speaking, analogous to doing degenerate perturbation theory in quantum mechanics, except your Hamiltonian is not Hermitian. So you can write your diffusion matrix sort of in this way, where this is matrix, sort of basically susceptibility matrix written on a different basis. And both this and this are positive by thermodynamic stability conditions. So unlike sound waves, diffusion modes can become unstable even in the CFT. So to give you a simple example, so here's the diffusion of 3 flavors with U1 cube. Let's choose DABC to be only non-zero if ABC is a permutation of 1 to 3. It's a convenient choice for Cartan generators. So you work in a state with all the 3 chemical potentials are equal to each other. And then what you can show quite easily from these hydrodynamic equations is like a 3-line exercise, is that the diffusion of the difference of charges, they decouple from the perturbations of sound. So usually sound fluctuations are quite sort of, I mean, a little bit messy because it's a scalar channel, everything couples to everything. But in this state, the difference fluctuations are going to decouple from everything else. And these difference fluctuations will have diffusion coefficients, which is the eigenvalue, one of the eigenvalues of the conductivity matrix divided by one of the eigenvalues of the susceptibility matrix. And so this eigenvalue of the conductivity matrix is going to be positive by positivity of entropy production. This is an eigenvalue of the susceptibility matrix is going to be positive by thermodynamic stability. So this was hydrodynamic fluctuations. Now let's do a little bit of holography. So everybody has their favorite way of showing pictures of holography. This is sort of my cartoonish or ducks and rabbits. So this is my cartoonish way of showing. A second. Yes. Yes, gravity pulls to the left. So this is the space-time where your quantum field theory live, n equals 4 super n mils. So this vertical thing is t, x, y, z. So it sits at the boundary of some larger space. There's an extra dimension which you call r, and in this extra dimensional space there is like a not a black hole but a black membrane with like a very large black hole with translation invariant horizon. So it looks like this. So this is what people call boundary. This is what people call bulk. And the idea of holography is that black hole thermodynamics that was worked out in the 1970s by Bardeen, Carter, and Hawken, and later by others, is supposed to be describing the thermodynamics of quantum field theory that lives on the boundary here. So if you want to do hydrodynamics, so what you do is you sort of look at perturbations of this membrane, and now you will have things like gravitational waves propagating in the bulk to the boundary, and hydrodynamics of this boundary theory is then interpreted with gravitational dynamics in this extra dimensional space, in this extra 4+1 dimensional space. So who lives in this 4+1 dimensions? Who lives in the bulk? So who lives in the bulk is determined by the field theory that you want to describe. So you have metric, because metric is related to conserved energy momentum tensor on the boundary. You have gauge fields, because gauge fields are related to conserved global symmetry currents on the boundary. And then you have other fields, as you know, what these other fields, they're different for different theories. They're required by the holographic construction. So who lives in the bulk for n equals 4 super n mils? So for n equals 4 super n mils, okay, there's going to be like an infinitely many fields that live in the bulk. So this is, I'm going to show like a simple truncation that is sort of relevant for the problem that I'm describing. So this is action is the integral of a Lagrangian square root of minus g. This is some prefactor, okay, just some prefactor. And so the thing is, so this is the Ricci scalar, Maxwell term, f squared for three abelian gauge fields. There's going to be Chern-Simons term required by the string theoretic construction of this, and there are various scalar fields, 3 scalar fields, capital X, and there is some potential for the scalar fields, right? So this is so-called STU black holes that people worked out in the late 90s as reduction of supergravity that is relevant for n equals 4 super n mils theory. Now, so you can sort of take this action, work out the equations of motion, solve for the black hole solutions. People did this. So don't, look at it. Okay, many, like many letters here, little letters, tx. Okay, this is a metric. Okay, so u is the extra direction. U is like 1 over r squared, or um, there's some dt squared, some dx squared, some du squared. Remember, u is basically r. So there is a gauge field, and there's some scalars. And the thing is, when you solve differential equations, you have integration constants. So your solutions depend on integration constants. And then there are 4 integrations for relevant integration constants here, which I call T naught, kappa 1, kappa 2, kappa 3. These are integration constants that parameterize, the gauge fields in the bulk and the metric in the bulk. And these integration constants are related to temperature and the chemical potential of the field theory by these formulas. Okay, so the metric does not, so solutions do not exactly involve temperature and the chemical potential. They involve these integration constants. You relate integration constants to T and mu, like that. So if you do this, you can actually work out the equation of state. If you know this, you can work out the equation of state quite easily. So this is the equation of state for the energy density as a function of entropy density and the charge densities for n equals 4 supermills at strong coupling. So I first learned about this from Soren Starinets, who took this basically from Bernd Svetic and Sabra. But then I learned that people, actually wrote down this equation of states much earlier in late 1990s by studying thermodynamics of rotating branes in 10 dimension. So basically, once you have the equation of state, you can compute thermodynamic Hessians and see whether these Hessians are positive definite. So this is the region of thermodynamic stability in the space of these integration constants, kappa 1, kappa 2, kappa 3. So what is shown here is that the orange region is the region where the Hessian eigenvalues are positive and thermodynamic equilibrium is stable. Outside of the orange region, thermodynamic equilibrium is unstable. This origin here is 0 chemical potentials, all 0 chemical potentials. So this is a little bit of finite density here. And once you sort of decrease the temperature, eventually you will get to the surface, blue surface in that far corner. Blue surface is the 0 temperature surface. So this is the phase diagram, but not written in the phase, not shown in the space of chemical potential and temperature, but in the space of those sort of integration constants that are related to mu and t, like I showed. So this dashed line here is the line when the 3 integration constants are equal to each other. So the reason I'm showing this line is that because the geometry along this line is called ADS Reisner-Nordstrom geometry. So ADS-RN is a geometry that is most commonly used to model the effects of finite density in holography. And what you can see is that if you're going along this line of all 3 chemical potentials equal to each other, eventually you will move to a region that is thermodynamically unstable. So it is thermodynamically unstable. You will not be able to see this instability if you just look at the determinant of the Hessian, because 2 eigenvalues actually change sign here. So if you look at the determinant actually stays positive because there are 2 eigenvalues that change sign. You have to look at individual eigenvalues. So yeah, so the lesson here is that it's sort of dangerous just to model the effects of finite density in holography by just using a simple abelian gauge field in the bulk. So what is the physics of this thermodynamic instability? I just said, okay, eigenvalues of the Hessian go negative. So what does this mean? Well, there are 2 options. One is that this is actually the end of the phase diagram. It's like the free theory with finite chemical potential. There is no equilibrium state. That's it, nothing. Another option is that it's actually a new phase, but what that phase is, it's sort of unclear what the phase is going to be at low temperature, high density. Now, this is actually not the onset of a superfluid transition. So often in holographic models, you have this phenomenon of quote unquote holographic superfluidity conductivity, which is sort of natural. They have bosons at finite chemical potential. They want to condense. But this is not what is happening here, because these superfluid transitions in holography are mediated by complex scalar fields in the bulk, but there are no complex scalars here. There are only real scalar. And recently, Alex Buchel looked at the effect of superfluid transition in this model, and it happens sort of not in this model, but in n equal 4 supermills theory, and it sort of happens at even lower temperature. So it happens, like somewhere here. So before you even get to that superfluid transition, you have You have stuff that's happening and you don't know what it is. So that was holographic thermodynamics of n equal 4 super n meals. Now let's do holographic hydrodynamics of n equal 4 super n meals. Now this is a picture of holographic cartoon of holographic hydrodynamics. So now you have nonlinear equations in the bulk for the metric, the gauge fields, 3 abelian gauge fields, and the scalars. And the equations are quite complicated. Okay, nonlinear PDEs, okay, complicated. Now you say, okay, this is too complicated for me. Let me linearize, work with linear equations for perturbations about this black brain background. And the equations are still complicated. Now you look at plane waves, and the equations are still complicated. So everybody who worked with like sound waves in holography knows that this is horrible. You can reduce this if you look at plane waves to ordinary differential equations, but there's like gazillion of them. They all couple to each other. You don't obviously see like any symmetries, and so it's horrible. But if you look at a state with all the chemical potentials equal to each other, then just like I showed you earlier in this example in hydrodynamics, in this state, the diffusion of N1 minus N2 and 2 minus N3 and 3 minus N1 decouples. And so what this means, there is going to be a similar decoupling in the bulk. So the fluctuations for like A1 minus A2 or A2 minus A3 or A3 minus A1, they decouple and they obey very simple equations. So this is something, this now becomes very tractable, and out of this horrible mess of equations, you have this decoupling, and now you can do stuff with that. So these are the diffusion modes of these difference fluctuations in hydrodynamics of n equals 4 super n mils. So the diffusion coefficients are the same as I showed earlier. Eigenvalue of the conductivity matrix, eigenvalue of the susceptibility matrix. Susceptibility matrix you know because you know the equation of state. So that is something you can compute. Conductivity matrix, in principle, you can compute, but we haven't. So we don't know this. In other examples, people sort of computed this and they found that these conductivity coefficients, they don't blow up, they didn't do anything fun, it's just some order one, well, order n squared times t numbers. So you expect that the bad behavior of this diffusion constant comes sort of from the bad behavior of this thermodynamic susceptibility. And remember, kappa is one of this, is the integration constant. The solution has 3 integration constants. I set them equal to each other. Kappa 1 is equal to kappa 2 is equal to kappa 3 is equal to kappa. So this is the imaginary part of the diffusive mode as a function of the normalized wave vector. So Q is wave vector divided by 2 pi t. This is frequency divided by 2 pi t, imaginary part. So this is the normal diffusion mode when you are in the stable region, and this is what it looks like if you are in the unstable region. Okay, positive imaginary part is a sign of instability, but then it sort of goes down and becomes, again, stable at large momentum. I'm not exactly sure what to make of this, but it does go up. Yeah. 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 I do not know, but what I can say is so if I showed that this sort of decoupling of this diffusion mode happens in hydrodynamics. No, I didn't demonstrate, but I just said that it happens in hydrodynamics. But you can also show that it happens to like all orders hydrodynamics. So it's not like in, you know, one derivative thing. If you just write down linearized constitutive relations to all orders, then based on, you know, SUN group symmetry, and rotation symmetry, essentially, you will have decoupling in a state with all chemical potentials equal. You can easily argue for the decoupling of those fluctuations. But I don't know if there is some kind of mathematical structure that underlies that. Well, I don't know if it does anything interesting. Yeah, yeah, yeah. Yeah. So the way I sort of understand this is that there is, so what I'm describing is a simplification that happens if you go along this line. There is simplification. So if you go along any other line that sort of crosses this orange surface, it's good. You again are going to encounter, negative eigenvalues of the Hessian matrix, but it's not going to be like a simple decoupling of those fluctuations. Some other fluctuations will become unstable, corresponding to the eigenvectors of the Hessian matrix. So along this line, the eigenvectors of the Hessian matrix look particularly simple. That's why you have this thing. But along any other direction, the eigenvectors of yeah. Mhm, mhm, mhm. Mhm. Great. So if you look at the picture of region of hydrodynamic stability, so it's the same picture that that you saw before, but I changed the title from thermodynamic stability to hydrodynamic stability. And now, so what you have along this dotted line is that you see that Reisner-Nordstrom background is unstable to perturbations of A1 minus A2, and so all the difference perturbations. So if you just have ADS Reisner-Nordstrom in a simple theory that only has a single U1, you don't know about the existence of these other things. But once you embed this in a larger theory, which is U1 cube, then this difference fluctuations, make the appearance, and they actually cause an instability. So also want to comment that this part here was studied before. Soren Starnias computed charge conductivity near this region here, and then in 2010, Buchel found an unstable diffusion mode numerically. So this numerical instability found there, okay, we can actually now understand this analytically. It's through the divergence of the susceptibility here and the finite value of the conductivity. That's it's here. So the next step, sort of missing from the analysis that I'm showing you, is that the computation of conductivity in this region here. Okay, so what have we learned? So you can do hydro with multiple U1 charges. So in holography, n equal 4 super-Yang-Mills is the simplest example. You can find analytic expressions for sound damping in terms of sigma AB. You can find analytic expressions for diffusion coefficients in terms of sigma AB. And the positive entropy production plus thermodynamic stability, they will give you positive diffusion constants. And positive diffusion constants means your charge wants to spread out. Thermodynamic instability can give you negative diffusion constants, which means charge wants to clump, so it goes the other way. And you will have simplifications when you want to embed it into larger G's. Now, so I want to finish with these statements here. So there's a qualitative lesson here, is that when you do holography at non-zero mu, it is easy to miss the fact that you are, in fact, studying an unstable phase. And there are a few questions here. So one question is that, okay, so what happens when you cool down this theory, which is, again, the simplest holographic theory? It's not exactly clear what happens when you cool it down to low temperature. Like, if there's a new phase, what exactly is this new phase? So I mentioned, BSQ hydrodynamics earlier. I don't know if it would be interesting to study holographic models for this BSQ charges. But then there are other things that you can sort of do theoretically. So computation of conductivities, this is something that sort of still has to be worked out here. And more generally, I talked about hydrodynamics associated with the Cartan subalgebra. but there's also this other non-abelian fields. So my holographic models only included the abelian fields, and so the hydrodynamic manifestations of the actual non-abelian fields corresponding to the SU4, that's, I think, something that's not exactly clear. So with that, I'll finish. Thanks. Where funny you should ask, because I think Gapser and Mitra back in the day, they actually did that for in one dimension less. um, this was before ABGM. Um, so for the purposes of field theory, the lesson is that instabilities you can even, so this is something that was sort of already in Gapser and Mitra, but I think got sort of maybe forgotten or not learned by people like myself, is that hydrodynamic instabilities can be found by looking at unstable thermodynamic directions in the Hessian. So this is sort of the statement that they had in ADS4, back in the day. Now, if you ask me about exactly the 10-dimensional interpretation of these instabilities, and if this is or in that case 11, I have not thought about it. This is the short answer. Is there anybody in the room who has no? Okay, but okay. So I know who to ask. Yeah. Yeah. Yeah, I don't have, yeah. So, I mean, look, this is Cyprian Mills. Once you start doing more like real world connection to QCD related to, flavor physics, arguably n=4 is not a very good, description. Yeah. So my interest was is that I just realized that, actually, if you want to understand the hydro of just the simplest holographic thing, n=4, there's still sort of gaps there that have to be filled. And so this is, yeah.
So when you show this plot of the dynamic stability,
Yep.
you have three axes.
Yep.
Kappa 1, kappa 2, kappa 3, which are the chemical potentials.
Yep.
Chemical potentials are those, what I got from your presentation, that those chemical potentials are related to the Cartan subalgebra
Yes.
of SU4.
That's right.
Dimension 3.
That's right.
All right. So why at the end of the program, there's three independent U1 groups?
Yes.
Why? What is the relation between these?
It's yeah. So that's exactly the reason, because U1 cube is a Cartan subalgebra of SU4, and so if I want to describe degrees of freedom associated with this Cartan subalgebra holographically, I introduce three gauge fields in the bulk of ADS. Now, in principle, what I yeah, look, I wouldn't connect it that much. See you also.
Take the Cartassa abaixo, vai uma billion through. It is completely equivalent to have three independent to one group.
Well, it is more restrictive. So if you have completely three independent abelian U1s, there is more freedom. Because all these things that I showed about, thermodynamic relation to this, anomaly coefficients and whatnot, this will not be there. So yeah, so this is like taking a slice through that subspace, through the space of all like three independent U1s. In principle, so order one estimate, yes. All of these supersymmetric theories have scalars. Something will condense at low temperatures. But what exactly will happen? May there be like a spatially inhomogeneous phase, before that or after that, superfluid? Like yeah. So the game. So figuring out low temperature phases in holography is actually a very tricky business. So for like one reason that I showed you here, you write down like a holographic theory and things seem fine, but then you add one more thing, it completely changes the phase structure at low temperatures. And then you add one more thing that may do like even more sort of drastic things at low temperatures, right? And in principle, you have many things, infinitely many things once you do dimensional truncation. And so yeah. Mhm. Yes. So superfluidity in ADS-FT was sort of the idea was put forward by Gapser in I think 2007, and since then, there's like a whole. The words that people put to it is holographic superconductor rather than holographic superfluid, but it's a superfluid. Uh, uh, right. So. Yeah, I don't know the exact paper that you mentioned. Maybe you can tell me the paper later. So what I one question that I sort of wanted maybe to comment on is that yeah. So this recent paper by Buchel, sort of he comments on that, and he comments on the relation between between the superfluid instability and this instability here. But again, in order to see superfluid instability, you have to have extra degrees of freedom, complex scalars. So you add these complex scalars according to the consistent truncation, and then you see what the effect is. Yeah. Good question. Yes. Well, for n equals 4, we have the Hamiltonian. But you add the complex scalars that are there in the reduction. of supergravity, right? So once you do the reduction, you will find complex scalars, and you know they will do something. Yeah. Mhm. Yep. Mhm. But the equation of state, right? So the equation of state will be sensitive to whether it comes from SU2 or just or U2 or just two. Yeah. Well, yeah. That's correct. That's correct. So one way to look at it is to evaluate what the energy momentum tensor is on the boundary, and read off the equation of state from there. Or another way is to look at the sort of partition function, which is like the on-shell action in the bulk. Or you can just look at, you know, just old-fashioned black hole thermodynamics that was developed in the 70s. And so it's kind of old-fashioned black hole thermodynamics just sort of gives you an equation of state. It doesn't say, or extra dimension, not extra dimension. This is some equation of state. Yeah. Mhm. When when holographic correspondence sort of first appeared in the late 90s, there was lots of hope in the community that it will if not solve QCD, then it will contribute significantly to understanding non-perturbative QCD. So this hope, well, this didn't materialize, but people did learn interesting qualitative lessons. So there are holographic models that get rid of conformal symmetry. Of course, there are confining holographic models that actually do have genuine confinement, not N=4, but more complicated models. You can also reduce supersymmetry. What you do not have typically in these holographic models is asymptotic freedom. So you capture the strongly coupled region, but not the weakly coupled high energy part. And so if you can convincingly argue that your physical problem is not, sensitive to asymptotic freedom, then yeah, you can sort of make statements. However, what I wanted to say is that I didn't want to advocate this as a sort of precision sort of test, or not test, as a precision sort of tool to study QCD. I wanted to advocate this as it's like the Eisen model. You don't necessarily solve Eisen model if you want to understand, phenomenology of a particular, alloy, right? So you want to study Eisen model because you want to figure out how things work first, right? And so that's what I'm doing here. Yeah.